So today I will talk about this topic of many-body localization and then seeing regimes where thermalization of quantum systems can fail. Okay, and then by the end of it, I hope to finish my talk in time. I will show you some experimental data that we have been collaborating with some experimentalists, showing the regimes where many-body localization can happen. Okay, so before starting the talk, I want to acknowledge the collaborators before I forget them. So I have a couple of papers in this topic, and then Marcus Rigol, Chen Chen, a former postdoc, Zhi Cai, Professor Fan Han from Chinese Academy of Sciences, who is responsible for building these superconducting qubits platforms that we are collaborating, and Professor Wang Haoha from Zhejiang University and Gao Xianlong. So, many-body localization and thermalization. So this is a topic that has been under study for the past few years. There are 2,000 papers in the past, I don't know, 5 or no more, I guess now. But the past 6-7 years, there are 2,000 papers on that. And then it's an interplay of experimental results, some analytical predictions, and also numerics that have been playing a huge role in the investigation of this phenomenon. And on top of that, I will try to argue today that numerical calculations can help us understanding and predict some phases that one can see experimentally as well. Okay, so I won't complete this topic. If you want to have a bigger and wider introduction about it, you can see some reviews that are recent reviews on the topic. They are quite complete. You can get a good picture of it. And on this topic, I have a handful number of papers that you can check. I'll mention in passing some of those, but I'll try to give you a bigger picture, since it's a colloquium, rather than my particular works on it. So to set up the stage, before talking about many-body localization, let me just remind you guys about localization, Anderson localization, which is localization of non-interacting particles, which was a problem introduced by Philip Anderson in 1958. That he proposed this quantum model that you have some kinetic energy and then particles, quantum particles hopping in different orbitals with some amplitude probability Tij, tunneling amplitude Tij, and then you select these orbitals to have disordered on-site energies. Okay, so if you take from these on-site energies from random distribution, from flat distribution, you can see that the amplitude of this disorder that introduced leads to localizing of wave functions, localization of wave functions. So he did this using perturbation theory in the regime that this disorder magnitude is much larger than the hopping amplitudes. But if you read the paper, he recognized himself that the paper looks like an unrecognizable monster. It's a very hard paper to read. But the main message that he was able to show is that depending on this disorder magnitude, localization ensues, which means that you have exponentially localized wave functions in real space. Okay, and then later on, they have shown that in 1 and 2 dimensions, any amount of disorder that you introduce in the system leads to this exponential localization for all the states in the spectrum. For 3-dimensional systems and above, one can have this possibility of having what we call mobility edges. So these are critical amount of energies which separates these 2 regimes of this quantum system, where you have localized wave functions in some part of the spectrum and extended one in another part of the spectrum, given that the energy is above this threshold here. So this is not only a very creative idea of a brilliant man, but also has been realized experimentally in the context of cold atoms. So if you have a cloud of atoms which are trapped by laser beams, and they are put together with this parabolic confining potential in the initial preparation, you can create a Bose-Einstein condensates using these rubidium atoms here, that if you remove this confining potential, you see that the wave function, this macroscopic occupancy of the single momentum, the Bose-Einstein condensate, displays this exponential profile in real space once you're in the presence of this disorder potential here, this speckle disorder. So this is an experimental verification and a realization of Anderson's idea of localization. But this has also been shown in other contexts, even in photonic lattices, okay, which is a combination of this waveguides here, that if you shine light at one side of this photonic lattices, diffraction would allow you to have like a spreading of this waste of your being. But if you have these waveguides having refraction indices in a disordered fashion in real space, you see that the integrated profile of the intensities also becomes exponential in real space, right? So you have diffraction that it's not fully accomplished because localization occurs here, okay? So this can be understood in the context that you transform the wave equation for this electromagnetic field in the Schrödinger equation at some regime, okay? But one of the interesting things about this scaling theory of localization was that if you're in 1D or 2D, in principle, any disorder localizes the system. So if you want to talk about an experiment, it's quite hard for you to say that you're starting from an ideal case and then you have some disorder to see the transition occurring. Because experimentally, any disorder will be unnecessarily there. It's impossible to prepare a really clean system. So there's another model which is somehow related to it, but it does not have completely random disorder. Quite on the contrary, it's fully deterministic, and it's given by this what's so-called Aubrey-Ender model, where this epsilon I, this on-site energies, they are given by this expression here. But if you take these beta values here as irrational numbers, a finite system size would never have energy values which repeat. So one says that we have a quasi-disordered system, and also it displays localization of the Anderson type, but there is a critical value of this amplitude of this potential here, delta, that turns the system into a localization. And this was also realized in the context of optical lattices, that one prepares, as before, a cloud of atoms in the center part of your trap, and then you, depending if you have a strong disorder here or not, this cloud of atoms can expand if you don't have disorder, or it becomes localized if you have strong disorder. So here are snapshots in time that you see that this cloud keeps localizing in real space. But then, what is the role of interactions? That's my main concern here. And that question, like what is the influence of interactions in these results, was thought by Anderson himself for like decades. And then from 1958 until 2006, I would say, there was some understanding that what could happen, but anything that was precise and quantitative was not known by then. And there was a paper then later by Basco, Alainer, and Schuller. What they did was the following. They started with the Anderson problem and include interactions in a perturbative fashion. And they managed to show that there is a way that include perturbation theory of all orders, meaning there's a convergent series in the perturbation. And they show that if you have large enough temperatures, this localization that you have originally is gone. The system acquires a finite DC transport. Okay, so this can be seen as perhaps a mobility edge, but in the many-body sense, there's a finite temperature that you can convert at finite mean energies, where the system becomes delocalized in the presence of interactions. And this was the most known characteristics of this many-body localization process, that you have the presence of these two knobs. One is disorder, and the other is interactions. And interactions in this regime is not like Mott localization that is a localization due to interactions, but rather interactions is the ingredient that allows the system to delocalize. Okay, so here's a bit of a hand wave picture of what's happening here with my poor PowerPoint skills, so sorry for that. So suppose that you have two exponential localized wave functions correspond to two particles. So if you have hoppings here in the system, these are not sufficient to overcome this exponential localization, right? So the probability of a resonance to occur, it decays exponentially with the distance between these two guys. But once you have interactions, these allow these two localized particles to see each other, and they can overcome the localization that comes from these on-site potentials that they have. So essentially it allows this mass transport at high energies, and then essentially if interactions are large enough, you would say that you give enough energy to the system, they can enter in resonance modes that localization is gone. Okay? So, and then the most important thing is that this is a completely isolated system. You don't have to connect it to any bath for this delocalization to occur. So the system delocalizes under its own influence. Okay? So, but then if you think about it, if I have another knob, which is disordered amplitude, if I crank it up even more, localization might still be restored. Okay? So as I said before, these are the two competing knobs that define the fate of the system. interactions, the localized disordered magnitude localizes. So depending on this interplay, you may have many-body localization or thermalization. Okay? So this was also realized in the context of cold atoms. Since you have control of interactions that you have between these atoms, which are trapped by laser beams, you can use this as a paradigmatic problem for studying many-body localization in the presence of interactions. So what is done experimentally? They want to measure absence of mass transport, okay? And for you to, the easiest way for you to do so is, as you have done before in the absence of interactions, is that you prepare some initial state and you want to see whether this initial information that you have encoded there is preserved or not, right? So in the context of cold atoms, what they do is that they prepare some, let's say, some charge-dense wave, okay, of your atoms. They just reside in some, let's say, odd sites of your optical lattice here. And they see whether this charge-dense wave, if they allow the system to evolve, right, is preserved or not. So here, when the average density is homogeneous over the lattice, one says that the system is thermal, not many-body localized. Or when there's still some information encoded here, the system displays many-body localization. Okay. So it's essentially a quench problem, and then the many-body localization manifests itself as a ergodicity breakdown. So how that was done experimentally, there was a paper by Manu's Bloch group in 2015, where they emulate the physics of this Hubbard model in the presence of this Aubrey-Ender potential, this quasi-periodic potential. Okay. So what is this Hubbard model? They, as I mentioned before, you have these hopping amplitudes between for atoms to hop on valleys of this optical lattice. You have disorder given by this quasi-periodic potential, where you combine two optical lattices with different wavelengths, okay? And you have some interaction magnitude here that you can tune via what they call Feshbach resonances. So these are all knobs that you have control of, okay? And then what they managed to see was the following. If you prepare an initial state, that is this charge-dense wave, and you quantify this imbalance, this survival of this charge-dense wave, you can see that for finite interactions, usually this imbalance is not surviving. You have homogeneously distributed atoms on the lattice. But if you keep cranking up disorder, you recover many-body localization. So that's the signature, the experimental signature of this phenomenon. So just one quantification of this. Here is like the imbalance, which is defined this way: density in even minus density in odd sites as a function of time. And if disorder is vanishing, if there's no disorder, this imbalance, which is originally 1 at the initial instant of time of preparation, it goes to 0. But if disorder is large enough, this imbalance is partially preserving. Okay? Yes?
What's the temperature?
So that's the whole thing, which is very, very funny. So how do you define temperature in this isolated quantum system? Right. So temperature is you define when two systems are in thermal that put in contact. They have the same temperature when there is no flow of energy anymore in the two of them. So here, this system is a system which is isolated. Okay. The way we define temperature is by just knowing what is the mean energy the system has and inverting the relation that the mean energies relate to the exponential of minus beta e and the eigenvalues of the Hamiltonian. So usually what we say here that this localization occurs at infinite temperatures. Okay, so that's the terminology that we like to talk about. Okay, it sounds funny, I know, but the very concept of temperature is funny in these isolated quantum systems. Okay, so very good question, by the way. But what I can tell you is the following: we're not discussing ground state physics. It's far away from it. Okay, so that is more easy to digest, perhaps. So this whole scenario here that people have done in this context of 1D optical lattices was extended in other experiments by the same group. So they became creative and they realized, oh, we can do this for not only 1D systems, perhaps 2D systems, okay? And they had a original paper which employs somehow the same protocol, which was the following. They have a two-dimensional square lattice they try to emulate the physics of this Bose-Hubbard model, have these atoms which are interacting, hopping around in this square lattice formed by this counter-propagating laser beams. And what they see is that instead of forming like an imbalance, like a charge-dense wave, they prepare in a way that the atoms just occupy half of their lattice. They have this semicircle occupation of the atoms. And they see whether the semicircle that they have originally prepared after the quantum quench, after the evolution of this quantum system, if you release the constraint that makes them occupy this half part of the system, whether these atoms, they propagate to the other part in the presence of disorder. So here the on-site valleys of this optical lattice, they are also disordered. They have some distribution. Here it's not flat, there is some Gaussian-like profile. And what they see is that if you have no disorder, like delta equals 0 here, here's our time snapshots of the system, this semicircle distribution starts growing and become occupying mostly of your whole lattice. One argues that the system is thermal, is ergodic. Essentially, this initial information that was encoded there is gone, right? But if the disorder amplitude is large, you see that there's still some difference between these two plots here. Some initial information is still encoded at long times, signifying that the system might still display many-body localization. There's a huge dispute in the field. There's a bunch of smart guys fighting of whether or not this result should be trusted or not. But some early experiments in the context of many-body localization, two-dimensional systems. Okay, and these guys went creative. They started publishing a lot of papers about that. They did this Aubrey-Ender model, this quasi-periodic potential that you have in 2 dimensions. So what they see is that they prepare initially this zebra pattern of atoms. Okay, they have atoms in every other line of this optical lattice, and they see whether this zebra that you have prepared survives or not the quantum evolution. If it does survive, there is still a finite imbalance at long times. One says that the system displays localization, displays this absence of mass transport, or not fully developed mass transport. So that's a signature of many-body localization. So I want to highlight here just one aspect of this localization here is that once you're approaching the transition between thermalization to many-body localization, the system has this influence of these rare regions, which are known as like Griffith's phases, okay, which the disorder there in those sites in space, in regions in space, is it's small in comparison to the total average. And in this regime, this imbalance and transport as a whole displays subdiffusive behavior. And one can show analytically that in this case, this imbalance displays this power law decaying time, which I will be showing later in my talk as well. Okay, so this was seen in the context of optical lattice, code atoms in optical lattices. And then it will be seen as well using superconducting qubits. Okay, so good. So what is the essence of MBL? So if you get not convinced, yeah.
Sorry, one more thing. Can you go back two slides to the first 2D experiment? Why they go on? So that's delta is 30. And how do you determine this delta critical in the second figure?
This you don't. So here it's not shown here. It's not like just a cute plot. But what they do is the following: they define an imbalance. Let me show this formula here, and then you get convinced. They define an imbalance, which is the occupancy on the half side, left side of your optical lattice, and on the right side. And they try to plot this imbalance here, this quantity, that they quantify this all images here, right, in a number, as a function of the delta, and they see that essentially has a behavior. Is there like a marker here? Yeah. So I can write here, right? So they see that there is a behavior that is like this, with error bars, experiment. It's something that behaves like that. So there is some critical delta C above which the system has a finite imbalance, and one says that this is the critical disorder amplitude. Okay.
For a certain finite time.
For a finite time, that's a very good point. So the longest time that they can achieve before, they start losing atoms from the trap, before, environment plays a role. So all this phenomena that I'm talking about here, I want to avoid the maximum that I can, that the coherence and effects of the environment as a whole play here. Okay.
That's in seconds.
That is not in seconds. That's in tunneling times. Tunneling time. So 1 over j. J is the hopping times. Okay. So do I have any seconds in somewhere here? No, I don't. I just having hopping times. But yeah, these are pretty long, like 100 hopping times. So that's coherent dynamics is pretty much gone in this kind of times. Okay. So if you're not convinced about all these experimental results, I can give you some small interpretation, or the most agreeable one of what is the essence of the many-body localization phenomenon. At least when it comes from the strong disordered regime, there is some consensus, hopefully, because there's a lot of society in this field, and the idea is the following. We know Anderson localization, and we all agree with it, right? So the idea is to come from the Anderson localization and slightly putting some interactions there and seeing the regime where this localization is still robust. So for that, what I do here is to just recall like this. Let's start with this model here. It's the 1D interacting spinless fermions on a chain. And they have some hopping amplitude. These particles can hop around. You have some interactions, contact interactions. And on top of that, you have this disordered amplitude. If you do some Jordan-Wigner transformation, you can equally investigate instead this random field XXZ spin half chain. Okay, so there's nothing much fundamental from here, but this is going to be easier for us to convince ourselves that many-body localization occurs. So on this, what happens is that you have this Zeeman field here, which is random, right, for these spins. But there's a direct mapping given by this transformation between these two models. So taking from this spin model here, let's suppose, for instance, that we take this exchange, which have x and y components in terms of the Pauli matrices. Let's put this to 0. We all agree that what remains here, this second term, it's a non-interacting model, which is easy to believe that localization occurs. Essentially, it's Anderson localization, right? If you have a random Zeeman field. And what are the integrals of motion here? Well, we know that the states, the eigenstates of this Hamiltonian are essentially product states, are the Fock states, right? And then you say that each one of these sigma iz are commuting with the Hamiltonian, which means that they are defined as integrals of motion, which means that you have an extensive number of integrals of motion, and then the system is integrable. Okay? If you translate it back to the language of spinless fermions, which means that the density in each one of those sites is a conserved quantity. Okay? And we believe that in this regime of emerging integrability, the system is localized. But then, what happens now if you start putting some interactions here, which is putting back this term to be finite, but still in the regime that localization is still very strong in comparison to the actual magnitudes of these exchange terms. What happens now is that one can try to find, or being brave enough, to diagonalize this Hamiltonian, okay? And then, if you diagonalize this Hamiltonian, you can find some unitary, quasi-local unitary transformation, such as that you dress these local degrees of freedom, these local integrals of motion, by the eigenstates of this Hamiltonian. And the most important thing is that these guys here, these new dressed local integrals of motion, they commute with the Hamiltonian, and they commute in such a way that they have a profile in real space. Okay, so they have a combination now of many terms that involve one integral of motion, two integrals of motion, and up to n. But the amplitude of these terms here decay exponentially in real space. Okay, so if you believe in all of that, what happens that this MBL Hamiltonian, the many-body localized Hamiltonian, is a Hamiltonian that has all these sort of terms involving one integral of motion, 2, 3, and n, but in such a way that these coupling parameters between these different integrals of motion decays exponentially, okay, with the distance between these sites I and j. So in this regime, one says that many-body localization is robust to interactions. So if you have strong enough disorder and this decaying profile of these exchanges between these integrals of motion is like fast, this decay is fast, localization still occurs. Okay? Good. So that's one of the most technical slides that I have in my talk. If you manage to digest that, I think from now on will be easier. Questions? No? Okay. Yeah.
Can you go over the quasi-local integrals of motion?
Yeah, so essentially what I'm trying to argue is like this tau iz, right? Essentially it's the following. You start from the product states, right? These guys, you know, these are integrals of motion. One can define this tau iz by dressing them, dressing the sigma iz's, the local integrals of motion, by the eigenstates of the Hamiltonian. You see, you're dressing, so this U here is a matrix that diagonalizes the Hamiltonian. Okay? So this is called this L-bit formalism that for the ones initiated in the many-body localization phenomenon, it's almost in every paper about it. It's somehow agreeable that this explains, in the limit that is very strong disorder, whether localization occurs or not. Okay? So now let me just point out another important result of this phenomenon of many-body localization that I'll be showing later that experimentally occurs as well, which is the following. If you do, let's say, if you compute this entanglement entropy, you divide your system, let's say, in regions A and B, and you compute this reduced density matrix here, rho A. And if you do like in a quench problem, as you have done before, like the experiments have done before, you initially prepare some initial state and let the system take care of the unitary evolution of this initial state. You see that this time-dependent entanglement entropy here, it grows as a log t. So it's the slowest possible monotonic growth one can get in time, and it occurs once many-body localization occurs. If you're in the thermal region where many-body localization is not there, the system usually displays this fast growth of entanglement entropy, which is in general power law in time. Okay, you have diffusive behavior here occurring. So this is another signature that can be tested experimentally to see whether this this phenomenon occurs or not. Okay, so this is all numerics, but one can see this in other contexts as well.
You don't have temperature.
Again,
When you talk about the entanglement entropy, is it involving
all the spectrum, all the spectrum. So that's another way for you to say, oh yeah, this is infinite temperature. I put them with the same weight. They all enter together. I'm not, talking about zero temperature.
So you cannot get this signature only looking at the ground states.
So in fact, this is another thing which is important. Even in the absence of disorder, in clean systems, usually if you compute this entanglement entropy, they follow ground states in general. If they're gapped, they follow this area law, right? They scale with this L to the power of d minus 1. D is the dimension of the system. But excited states do not. Okay, they follow volume law. So this exponent here is d, not d minus 1. But what happens that in the many-body localized phase, you recover even for excited states the area law. And that's the reason why, like methods that like DMRG and matrix product states and the likes, they work well deep in the many-body localized way. They need that the system doesn't have a very large entanglement entropy, right? If it's volume law, it doesn't work because you're cut by the bond dimension. Okay? So that was a good question as well. Okay, and another way that one can characterize this onset of the many-body localization is by analyzing the ergodicity of the system, which can be easily seen by, if you're brave enough, if you diagonalize the system, you get all the eigenvalues, you get the spectrum of this Hamiltonian. And you see that if the system displays thermalization, these eigenstates, these eigen energy levels, they repel each other. There's some characteristic distribution of the ratio of adjacent gaps. So suppose you get your eigenspectrum here ordered. You take two consecutive gaps in the spectrum and take the ratio of the smallest to the largest. Get a bunch of values of this ratio here. Make a distribution, you see that this distribution follows something from the theory of random matrices called the Gaussian orthogonal ensemble of random matrices, which means the following. The probability of finding two states where R goes to 0, meaning that this minimum value here between these two gaps goes to 0, is 0. So degeneracies are avoided. So you have level repulsion occurring here. Okay, so this is a thermal system. But once you put disorder, this level repulsion starts getting washed out. And essentially, if you have strong enough disorder, so I have different curves here. I'm increasing disorder amplitude up to this sine curve here. What you see is that this level repulsion is completely gone. And the system is said to be many-body localized. So that's one of the easiest ways that you can see this phenomenon occurring in the context of simulations that allow you to obtain the eigenspectrum of these Hamiltonians. Okay? So this is one another aspect that I will show also working in the case of, well, it was done even here by one Dimitri Angelakis. They did this in the context of superconducting qubits. Use the same analysis to show that many-body localization occurs. So this is a generic phenomenon that is believed to occur in many different systems. Okay, spin systems, even the Hubbard model provide that you break some SU2 symmetry. And generically, it works like this. You have some interactions and some disorder amplitude. Disorder amplitude large enough can overcome the thermalizing effects of interactions. So this somehow believed it occurs by some. And it has some few generalizations that have worked, but I will not show details. If you suppose that instead of having these random scalar potentials that generate disorder, you introduce random vector potentials, okay, suppose you have some flux in your lattice that are disorder, these are not strong to overcome the thermalizing effects of interactions. So if you have a random flux model, this does not lead to many-body localization, okay? Other studies have shown, including one paper that I have done 2 years ago, that many-body localization can still occur in translationally invariant Hamiltonians, even in the absence of quench disorder, provided you have very funny and engineered Hamiltonians, which are not only creative, but can also be simulated and emulated in the context of cold atoms, like in these optical lattices, which are embedded in cavities. These cavities, they have these photonic modes that allow like these atoms at very long distance to interact. And if you have some frustration occurring in these interactions, and the interactions are large enough, many-body localization still occurs. Okay, so going back to the standard MBL problem, and the huge fight in the field to agree or not whether these mobility edges that I have mentioned in the beginning occur. So here it's one of the phase diagrams of one of the nicest papers, a numerical paper on the many-body localization for the Heisberg model in the presence of this random Zeeman field. And they show here these two axes. So the x-axis is the disorder amplitude. So how much disorder is the Zeeman field? And the y-axis here is the energy density. So somehow you take the whole spectrum and you renormalize to be in between 0 and 1 here. Okay? So what they see is that if you're sitting at some disorder amplitude, let's say around 3 here, this small energy in the spectrum, they display some sort of localization, MBL. And the middle part of the spectrum seems to be ergodic, delocalized, right? So this has been seen in other numerical works, in other models, related models. This general trait of this D-shaped structure also occurs. But there are some people that says that this should not essentially occur, okay? I will give some general argument of what they talk about without going to details. But these guys, they say that mobility edges are not possible. And the argument follows like this. Suppose that you have some system, okay, that you have some state describing this system. Usually is an overlap of many of the eigenstates of the Hamiltonian, right, with different weights. But suppose that you have some of those weights corresponding to thermal states, states which are extended. These thermal states, they essentially behave as a bath to the localized states. So if you wait long enough, this bath would delocalize the whole system. Okay, so this is called this bubble growth of this bath argument that leads to what they call thermalizing avalanche. The many-body localization itself, it's not robust to the presence of these hot bubbles. Okay, so if there is a many-body mobility edge, the argument goes in the hand of many-body localization shouldn't occur to begin with. Okay, it's a not robust phenomenon. So it should not occur in the thermodynamic limit. And then what they say is that all numerics have done so far, they are influenced by finite size effects. Okay, so then, well, going back to the topic of many mobility edges, this was done even in the absence of interactions. There was this paper. I keep seeing there is someone proposed to put this figure here on the wall. That mobility edges occur in the 3D Anderson model, realized in this context of cold atoms. Also in the 1D generalized Albrecht model, so mobility edges can also occur. But once you put interactions, this is less known. There was another paper by Manuel Bloch, but they tried to see these mobility edges, and they somehow failed. Okay, so what they see here is the following. They show this imbalance as a function of time, okay, that I have mentioned before, for two models here that they can emulate using cold atoms. One is the Albrecht model that has no mobility edges in the absence of interactions, and the other is the generalized Albrecht model that it does display mobility edges. And what they see is that they cannot differentiate the two of them. So if there is some mobility edge occurring there, it doesn't allow you to see any discrepancy in the dynamics of these quantum systems. Okay, but then we got a bit like, oh, maybe they missed something here. And then we start doing some numerical simulations, and we analyze this type of Albrecht model as well, which is quantified by these hopping amplitudes here, decaying exponentially in real space, and you have this quasi-periodic potential here, telling how much disorder occurs in this non-interacting system. In the absence of interactions, you deal with a system that has a mobility edge. You have a fraction of the states which are localized, a fraction of the states which are delocalized. We take this smallest possible fraction finite of extended states. Okay, so you're in the verge of localization. And then you see whether this single particle mobility edge survives or influences the dynamics of the system in the presence of interactions. So we put contact interactions that I have described before, and I quantify this phase diagram using this measure of ergodicity, of how much these energy levels in these Hamiltonians, they repel each other. So I show here this phase diagram similar to that one that I have shown before of the energy density versus the disorder magnitude here, so V is disorder magnitude. And in the case that you have these exponential hopping profiles, you see this D-shaped structure that if you look at this disorder amplitude here, 8, there's a clear difference between different energy densities. Here, the system displays level repulsion or thermalization sets in, but at lower energy densities, that's not so. But this is not enough, right? An experimentalist usually, if the system has an exponentially dense profile, energy spectrum, one cannot compute these level spacings. So they're more interested in this quench scenario via this computation of the imbalance. So what we do is that we have a generalized imbalance. We compute an imbalance that is observable, which is uniquely tailored for the initial state you have. And since this system is isolated, the initial state encodes the whole energy of the system. So this energy, it never changes, right, since it is isolated. So we have an observable that is essentially one for whatever Fock state, for whatever product state you can come up with. And we see whether this information that I have encoded in this product state survives or not as a function of the evolution that follows from this unitary dynamics. And what I show here is this contrast between low energy densities, so epsilon around 0.1, and around 0.6. So here I'm looking at this point here and this point here. And I try to see the difference in this imbalance, which is signals a memory of the initial preparations as a function of time. And what we see is that essentially at low energy densities, this information survives at long times. Okay, while at the middle part of the spectrum, it dies off, right? So the different colors, they are different system sizes, and you see that as you increase the system size, this goes to 0, and this one seems to be finite still. But one can say, oh yeah, I still don't quite believe that. One has to do scalings of this. We did, and then it looked quite okay. But this whole idea of using different initial states as a way for you to investigate mobility edges has also been thought about, not done yet, in the context of cold atoms. So Emmanuel Bloch and his group, they started doing this simulation in this 2D Hubbard model that they have emulated before. They have this semicircle initial distribution of the atoms, and they look to other initial patterns here, like zebra patterns, another zebra pattern with different wavelength, and they try to see whether this onset, which looks pretty much like this, right? Onset of the imbalance at long times with the disordered amplitude depends on the initial state that you look at. But from their experimental results, it's pretty hard to differentiate those. So is there a way one can use this protocol of using initial states that correspond to different energies and see disordered amplitude being different to trigger the onset of localization in a more controlled way? Cold atoms are having a hard time. But then, since there is no much flexibility of the preparation of these initial states, and for that, it comes this new revolution that is occurring in this context of emulation of quantum many-body systems. And this is done in this context here of superconducting qubits. So here I'm showing a figure that you guys are collaborators, more specifically Professor Dimitri Angelakis. They have collaborated with Google in this quantum processor here. So they have 9 qubits. They managed to emulate the Hamiltonian of this Bose-Hubbard model. Okay, that in total they have 45 states available in this Hilbert space. So there was a bit of a criticism saying that since they have at most 2 photons here which are interacting via these resonators, one could not call this fully many-body localization, but perhaps 2-body localization. But they do manage to see something very interesting regarding this distribution of level spacings here that I mentioned, the ratio of level spacings, of gaps in the spectrum. That for small disordered amplitudes, it has this distribution here that looks like GOE, but once you crank up the disordered amplitude here that you have, it goes more towards this Poisson regime that is signature of many-body localization. So it was one of the first, or not if the first, experimental signature in the context of superconducting qubits to see the phenomenon of many-body localization. And things have moved fast since then. Google has published one article, and there's another one in archive that was put out in October, using the same platform, using 9 qubits, but now initializing more photons. That means that you have more particles there to interact, and see that essentially many-body localization is robust. So what they quantify here is these 2-body correlations. Okay, so essentially, if you have low disordered amplitudes, here these yellow curves, these 2-body correlations, so these density correlations here, they are long-ranged. So this is the separation between 2 points in space, or 2 qubits that you're measuring the correlation, and it's finite, and it spreads over the whole system. But on the other hand, if you have disorder that is strong enough, these 2-point correlations decay exponentially. So this is a signature that many-body localization does occur in this 9 qubits platform here. Okay, so then there was another recent paper that this shows that this whole platform of superconducting qubits is scalable, and Google has published this paper using 53 qubits that tries to tackle some fundamental aspects of quantum supremacy, which is not exactly the topic of this talk, and they don't try exactly to investigate this phenomenon of many-body localization, but I figured that it would be important to highlight this for you. So using this as a motivation, we collaborated with a group in China that they have a platform with 20 qubits, and they can emulate this Hamiltonian, which is similar to the Hamiltonian that Google can emulate with this 9 qubits platform that they have. That is this, you have like 20 qubits which interact with each other with direct couplings, and on top of that you have a resonator which couples these qubits. So in the regime that these qubits here, all 20 here, there are 10 here, 10 here. The regime that these qubits, they have this resonator being prepared in the ground state, meaning that you don't have modes, photonic modes in this resonator here. one can say that this Hamiltonian can be mapped in this other one here. Okay, so this other Hamiltonian looks like a spin model, like with exchange m and n quantifies different qubits, and some disorder amplitude that you can insert by change the local frequencies of each one of these qubits. And if you look at this Hamiltonian, you can say, oh, look, but this is quite funny. That looks like a non-interacting Hamiltonian, right? You have just some exchange here, some local disorder amplitude. But what happens that these couplings here are not nearest neighbors. They are long-ranged. So if you translate back to the language of spin-length fermions, this has all these strings operators that essentially renders a non-integrable system even in the absence of disorder. Okay? And then we emulate the physics of this model. They are able to quantify precisely the couplings between all these 20 qubits. And then at the end of the day, we had one qubit that was a bit faulty, like in Google. They had 54, 53 worked. We got like 19 working well, and we were good with that. And after some initialization, what we do is the following. We can excite some of these qubits from like the 0 to the 1 state, and we prepare initial Fock states that in the presence of this disorder can display localization or not. So this is our protocol. And we show here some phase diagrams that I have shown before in the context of numerical simulations, but now using experiments. So what I'm showing here is this, the color signifies this generalized imbalance, okay, as a function of the disorder amplitude that we put for each one of those qubits, and the energy density. The different energy densities correspond to different initial Fock states that you prepare. And you see that this D-shaped structure is pretty similar to the one that one obtains using numerical simulations from the couplings J, M, and N that are experimentally measured. Okay, so that helps us in identifying that this superconducting qubits platform can realize, at least in a finite number of qubits, this edge here between localized and thermal states. So if you look at the statistics of level spaces, this somehow looks similar as well. And then on top of that, looking at the profile at cuts here in different energy densities, you see here that at the middle part of the spectrum, where epsilon equals 0.5, this initial information that was encoded, it goes to 0 at long times. So the lines are numerical data, and the markers are experimental data. But if you're looking at the smaller energy densities, this is no longer the case. And these dashed lines here, they correspond to what we call infinite time averages, which are obtained numerically. And if you're more interested, I can talk about it later. Okay? So in total, instead of having 45 states, our Hilbert space has something of the order of 100,000 states. So which is a bit larger and can show more like interesting physics as well. So here, just a snapshot, not a snapshot, but a comparison between experiment and numerics. One concerns the time evolution of this imbalance. So the color, again, signifies this imbalance for small, intermediate, and strong disorder. Okay? And then what we show here is that this first set of panels, these are experiments. These on the lower ones are numerical calculations, and they are mirror images. So the energy density goes in opposite ways for these two plots. So they should, the more they look mirror images, the more accurate is the quantification of these coupling parameters between the qubits, such as to identify this mobility edge occurring here. So what we see about, we argue about the mobility edge is that you see that the center part of the spectrum, where epsilon is around 0.5, this imbalance becomes more bluish, which means that it becomes close to 0, meaning that you have lost a lot of information of the initial preparation of the system. But on the other hand, at the edges is still reddish, which means that this memory is still a bit there. Okay. On top of this, we are able to identify another property about the many-body localization is that once you're in the verge of approaching the transition, you have this subdiffusive behavior of the imbalance, which is signified by this power law decay of in time. That if you compile all the different decaying exponents, they work like this. It means it seems like there are different disorder amplitudes at different energy densities, which trigger the onset of the many-body localization. Because at exactly this transition point, this localization length here goes to 0. Okay. So these are experimental results. The markers and the lines are numerical simulations of corresponding disordered amplitudes here. And then I'm ending my talk. I think I'm on time. This is perhaps the last slide for data. Is that we quantify something which is never quantified before, at least in the context of superconducting qubits, which is the participation ratio, which works like this. Suppose that you have some state and you have some basis. We quantify how spread is this state in the basis. Okay, so that's essentially the participation ratio. The basis we're talking about here is the Fock basis for this forming this Hilbert space, and we quantify this quantity here, right? The inverse of the sum of in all possible Fock states n of the square of the probability of finding the wave function in this Fock state. Okay, essentially this quantity here is chaos, is extensive, is the system is delocalized, this state is delocalized, but it should be not extensive if localization plays a role. We don't have access for the moment for scaling analysis. We have 19 qubits working. It would be interesting if you have like 19, let's say 25, 30, 50, and do some scaling to see whether different energies on your spectrum display a different behavior of localization or delocalization. But at least it's quite significant that you can see that at smaller energy densities, the participation is an order of magnitude smaller than in other parts of the spectrum. So it looks like if there is some localization occurring, it's much more robust here than here, right, at this disordered amplitude here, which is an intermediate value. And on top of that, the last experimental data we have concerns what we call the quantum Fisher information, okay, which is essentially, it looks like a variance of some observable. Here is, again, this generalizing balance. And it has been used before in the context of this quantum simulations as a minimal, as a witness of the entanglement entropy, okay? And then in this case here, at the low energy densities, also displays this log T behavior, this slow growth in time of this quantum Fisher information if you are at energy densities which are low enough. And then in the case that you're at the middle part of the spectrum, this grows faster, and then the log T is not as good as here as in this part that we believe displays many-body localization. So these are the results that I have for today. And I just want to highlight this many-body localization has all this hype about it. There are many big guys working on that, and provides some understanding about like fundamental properties of out-of-equilibrium systems, okay, which are isolated. They show that thermalization can be halted if you have disorder that is strong enough. And people have done experiments using optical lattices, using cold atoms to understand better this physics. And some numerical experiments as ours can provide some interesting information that can be used experimentally to probe still debatable aspects of this phenomenon. But this whole MBL is still poses like a computational challenge for classical computers, right? The argument that mobility edges should not occur goes to say that all the results that we have so far, they are affected by finite systems that one can tackle with classical computers. But quantum computers, they are not completely, but somehow, they are not completely challenged, they are not completely limited by this exponential complexity of the exponential growth of the Hilbert space. And they can go further, they can go beyond one can predict using classical computers, and perhaps settle this debate of whether mobility edges can occur or not. So that's what we hope. We hope that we can scale our platform to a larger number of qubits, and eventually provide more information of whether or not many-body mobility edges can occur. So one of the interesting applications of these results, if you're interested, is not only about a fundamental aspect of the quantum matter, but is that people have been talking about the many-body localization as a way to realize a quantum memory. Because if you realize what I've been talking in the past 50 minutes or 55 minutes, was that you have encoded some information in this quantum system, and you want to see this information being preserved at long times, right? What we show here is that one has to pay attention to the energy of this system, because if not, this information can be washed out if you're at energies which are large enough, right? If you're sitting close to this transition between localized and thermal states. So this is an important application of what I have been talking about here today. And that's pretty much it. I have just a small announcement. We have like positions for postdocs available in our center, in my group as well. So if you know someone, or if you're interested in yourself, please talk to us. And also we are very welcoming for visitors. We have some visitors like George. He comes often to visit us, and you're all welcome to come. And with that, I would like to thank you for your attention.